Okay, so we are now going to start the 10th section, permutation groups. Let us recall what we saw in the previous section, that is Cayley's theorem, the ninth one. Cayley's theorem states that if we have a group G, any group whatsoever, then there exists a permutation group A of S for some set S that has an isomorphic copy of G inside of it. More precisely, this means that there exists a subgroup G prime of A of S that is isomorphic to G. Group theoretically, there is no distinction between G and G prime. And in particular, if G is a finite group, then there exists a symmetric group Sn for some positive integer n, is the symmetric group of degree n, such that there exists again a subgroup G prime of Sn that is isomorphic to G if G is finite. And in fact, if one recalls the proof of Cayley's theorem, this set S, we took there as G itself. That means in place of S we took G. So if our group G is finite and has order n, then in place of A of S we would have Sn. So this fact shows that these groups A of S, and in particular the finite versions, that is the symmetric groups themselves, are quite important, because if we want to study about groups, then there is no real need to ever leave this class of groups, because if we study these groups and their subgroups, then we are actually studying all groups. Between two isomorphic copies of one group, there is no group theoretic distinction, so there is no point in studying these two things separately. And so it becomes necessary and important to study these groups themselves much more closely than we have studied groups so far. And because we are primarily dealing with finite groups in this text, so the symmetric groups become very important. And that's what the first paragraph of this section says. We have seen that every group can be represented isomorphically as a subgroup of A of S for some set S, and in particular a finite group G can be represented as a subgroup of Sn for some n, where Sn is of course our symmetric group of degree n. This clearly shows that the groups Sn themselves merit closer examination. So the section starts off like this. Suppose that S is a finite set having n elements. These n elements, some n elements, n number of elements, xi, where I varies from 1 to n. If phi belongs to A of S, because S consists of n elements, so A of S is the same thing as the symmetric group of degree n Sn. So that means if phi is an element in Sn, then what does it mean for phi to be an element in Sn? That phi is a bijective mapping on the set S. That is, phi is a one-to-one mapping of S onto itself. Okay, so now we think of how we can specify phi. Of course, there is a way of specifying phi, because after all phi is a function. We define or specify a function using some formula. So that's what the author is saying, and we can write phi out by showing what it does to every element, what it does to these elements, all of them. That is the usual way in which we define or write a function. One example has been taken. Say there are 4 symbols now, that now n is 4, which are of course x1, x2, x3 and x4, and the phi that we have now, which is now an element in S4, the symmetric group of degree 4, is precisely this function. It maps x1 into x2, x2 into x4, then x4 into x3, and x3 into x1. Then you can clearly see that phi in fact is a bijection, is a one-to-one onto mapping from the set of those 4 symbols to that set itself. Okay, this is something we already know. This is how we pretty much define any function, not just bijections but any function. However, since we are going to work with these functions, because we are going to study Sn more closely, so we want a more manageable notation than this cumbersome way of writing what phi does to every element. So Herstein is saying, but this is very cumbersome. Of course, this way of showing what the function does is nothing wrong, and in fact you can clearly see what phi does to every xi, but you have to see, you have to look closely to see what is happening. It's not like okay, let's just move forward, then we will see what the difference between this notation and that other notation is. One shortcut might be to write phi out as this. x1, x2, x3, like that it goes, and eventually we have xn, and in another row we have xi1, xi2, xi3, and so on to xin. And what we do, we enclose this array of symbols within round brackets. But what is this? What does it mean? Where xik is the image of xk under the function phi. Returning to our example, above, phi might be represented as this. x4, x2, x4, x3, x1. So what the author is suggesting is that instead of this type of this manner of showing what phi does to the x's, we can adopt a notation like this, where these symbols that appear in the bottom row, they appear in this manner. xik is the image of xk under phi. So this also shows what phi does to the xi's, to every xi, in this manner, that you look at the top row, there you choose some xi, say x3, to see what the image of x3 is under phi. You just look directly below it. The symbol appearing there is the image of x3 under phi, and in that manner we have all the other images. So the original elements appear in the top row and the corresponding images appear in the bottom row, which of course, because the function is after all a bijection from S to itself, this will be these elements only in a different arrangement. Okay, the order may have changed in writing them in the second row, or that is why this function is called a permutation. No, it has changed this original arrangement. Likely it has changed this original arrangement. Likely I say because if the phi is actually the identity function on S, then x1 will appear below x, that is, this one will be precisely x1, this will be x2, this will be x3. There will be actually no change in the arrangement. However, any other phi will change the arrangement, so it is some permutation. And you can now clearly see, in this notation, returning to our example above, this particular phi can now be represented like this. Image of x1 is x2, so it appears below that. That of x2 is x4. Image of x4 is x3. x4 is, oh, I think I have made a mistake, no? x4 is x3. x1 has image x2, x2 has image x4, x4 has image x3, okay, and x3 has image x1, okay. Yeah, now it's okay. So that way we have the bottom row. So the difference between this way of writing and this way of writing is clear. Looking at this, you can see at once what is happening. Here also you may argue that at once you can see what is happening, but this is much more compact, and it appears as a single object, a single arrow, as opposed to this cumbersome way of writing, which does not seem like a single entity. Although it is, but still the representation does not say that it is something that you can carry around in your calculation. This is much more convenient, and it shows at once what is happening. So now we move forward with this notation. Okay, now we are going to simplify things. This is not necessarily a simplification of that other way of writing. It's just another more compact way of showing the same information. But now we are going to simplify things further. While this notation is a little handier, there is still waste in it. Is a little handier there is still waste in it. That means there is something in this notation that we can remove and still retain the same amount of information, and that extra unnecessary thing is actually the symbol x itself. For the symbol x seems to be serving no purpose. So we can in fact remove a x. We would equally well represent the permutation, this general one, and then this one will also come. As this one, without bothering to even write x, we just look at the suffixes, because the suffixes only help us distinguish between the x's, right? Looking at these two symbols, we know what they are or what they represent only by looking at their suffixes. So it's enough to just write the suffixes. So that's what we do. And correspondingly, in the bottom row also, we write only the suffixes. Our specific example if we follow this simplification, would read this. So here also we do that same thing, and thus we get 1 2 3 4 2 4 1 3. Now it looks much more neat than this one. Obviously you can see that. Given two permutations, say theta and psi in say Sn in the symmetric group of degree n, using this symbolic representation, of theta and psi, what would the representation of the composition theta psi be? We need to answer this because when we are working in the group Sn, all we have to do is to compose elements, right? So if we are adopting such a new simplified notation for the permutations themselves, then we need to be able to also devise some rule for saying what the product would be in this new notation, because otherwise there is no point in writing the permutations like this. If we again have to go back to their original functional notation and then figure out ordinarily what the product is, and then again bringing the product permutation into this form, that if we have to do that, it will become useless, and there would be no point in just simply for the sake of writing a permutation compactly. This notation would be of no use, that is. To compute it, we could start and see what theta psi does to x1, of course. We could start and see what theta psi does to x1. In fact, we have to see what theta psi does to every xi, but first to x1. That's what we have to figure out. and because of our simplification, x1 henceforth will be written as 1, but in the background you should never forget that these are not ordinary integers, they are suffixes. So really we should think of this as the element x1 in the set S. The decision to write 1 in place of x1 is merely a simplification. Okay. Henceforth written as 1. Say first theta takes one to say k1, where you should understand that this k1 is also actually x suffix k1, xk1. The author has written I1, it does not, okay. Oh, but then he uses k separately. Okay, let's just go exactly how Herstein has gone in the text. Theta takes 1 to I1 and psi takes I1 to k, say. So truly these things mean that theta takes x1 to xi1 and psi takes xi1 to xk. Then clearly theta psi takes 1 to k. And this is how, of course, we will decide what the symbol for theta psi would be. I mean, what this type of symbol for theta psi would be, using the definition of the composition theta psi. Then repeat this procedure with the other suffixes. For instance, if theta is the permutation represented by this notation, 1 2 3 4 3 1 2 4, and psi by this one, You may sometimes wonder why I take so much time to clean the board. That is because if I somewhat sloppily just clean and some parts are left out, then the more we write and the more we repeat this process, the murkier it will become, and at one stage you won't be able to make out the texts. I have seen this happen before, so it's better to take some time and clean the board every time we use it. And psi by this one 1324, then according to how we would calculate theta psi using only these notations, theta takes 1 to I1, so here I1 is 3, and what is k? Psi takes I1, that is 3 to 2, so theta psi takes 1 into 2. It first theta first takes us from 1 to 3 and then psi takes 3 to 2. So we theta psi takes 1 into 2. Similarly, theta psi takes 2 into 1, 1 into 1, 2 into 1, then it takes 3 to 2 and 2 to 3. That means 3 into 3, and 4 of course is unchanged by both theta and psi, so it will remain unchanged by theta psi. So if we now use this same notation to write out theta psi, we would then get this, that is the representation of theta psi in our new notation is this: 1, 2, 3, 4. So 1 is mapped onto into 2, 2 into 1, 3 into 3, and 4 into 4. Okay. And in fact, this same thing can now be written without writing these intermediate things more compactly like this. I mean the whole calculation. We have gone through what how one calculates this notation for theta psi once in this way. So now we can write our, we can summarize this calculation like this, that is if theta is this, so we better start treating these symbols as the permutations themselves. And psi is this. Then theta psi is times and the result is this 2134. At first glance, it may seem like a pointless exercise to write the calculation like this, because you may think that you have to go through all these writings. Yes, you have to go through all these observations, but there is no need to write these things. If you just look at what has gone on here itself in this way, then you don't even have to think in this manner. That is, 1 gets mapped onto 3 and then 3 gets mapped onto 2. So 1 gets mapped onto 2. You can say it more quickly. 1 goes to 3, 3 goes to 2, so 1 goes to 2. 2 to 1, 1 to 1, so 2 to 1. 3 to 2, 2 to 3, so 3 to 3. And 4 to 4, 4 to 4, so 4 to 4. There is one more point here that I should mention. The thing is that you may have seen in some of the other videos that where we have actually gone through these notations, and we have in fact seen permutations. There you have calculated this product by starting from the right side and then going towards the left side. That is, you first see this one according to you, specifically in Galilean's contemporary abstract algebra. There the product is would be calculated, this same product, like this: 1 to 1, 1 to 3, so 1 to 3. According to Galilean, 1 would be mapped onto 3, not 2. This same theta psi is another mapping according to Galilean. That is because their function notation is like this. So if we are following Galilean's notation, or what we more generally use, then the calculation of theta psi on some input x looks like this. First we apply psi on x, and then on the result we apply theta. So first we apply this permutation on 1, that gives us 1, which is psi of 1. And on this one we then apply theta, which gives us 3. So Galilean would give you 3 as the output. However, here in Herstein's Topics in Algebra, this is how we are writing things, right? Our input lies to the left of the function. So that is why we first apply theta and then psi on the result x theta. So here in Herstein, the order in which you have to carry out this calculation is the order in which the permutations are actually appearing. That is, theta comes first and then psi. So you start here first and then psi. Okay. So you have to make sure which convention is being used in writing a mapping. That is, what mapping notation we are using. Because otherwise, without that convention and without you knowing exactly what this composition means, this composition actually is meaningless. Okay, so that's how we can calculate the product of two permutations in this new notation, which may not be all that new for actually any of us. But if you are seeing this thing for the first time, then it's of course new to you. This is the way we shall multiply the symbols of the form. Two such symbols will be multiplied in this manner. Such general symbols or any n and any of these possible permutations. Okay. But is there only just this much to this new symbol? Of course not. We are now going to go deeper and see that these symbols further can be broken down into some other types of symbols, which is not just merely a notational convention, but it actually tells us about the general structure of permutations themselves. So we start in the next paragraph. Let S be a set, a non-empty set actually, and theta be a permutation of A of S. This type of trivial things often are not mentioned by Herstein, because in the context of the things that we are doing, there is no point in taking S to be the empty set, because we are going to consider the permutation group A of S, so S is non-empty. Okay. So that means S is a non-empty set and theta is a permutation on S. We are now going to use theta to define a binary relationship on S, that is between any two elements in S. For any two elements A and B in S, we define a relation by which A and B are related, and this is expressed by writing a notation like this, that A is related to B or A is equivalent to B. Or if you want, you can write, because we are using this three horizontal bars, that A is congruent to B. A and B are treated as the same thing according to this relation, but because this relation, the way we are now going to define it, ultimately will depend on this theta, so we suffix this symbol with theta. Okay, A is related to B with respect to theta. If and only this is the definition of the relation. b is equal to a theta to the power I for some integer I. For some integer I. Now what does it mean actually? Let's first see that. We are saying that A is related to B if B is a theta to the power I. What is this a theta to the power I? Because theta is a permutation and theta is coming from this group, so no matter what the integer I is, we have a definite meaning for this theta to the power I. It's the integral power of theta in the group A of S. For example, theta square, you know what theta square is. Theta square is theta composition theta. Theta to the power minus 2, for example, you can view it because of the rules of exponent as the square of the inverse of theta, or equivalently you can also view this as the inverse of the square of theta. By the rules of exponent, see, rules of exponents are there and they can be used to interpret these powers in many possibly different ways, because we are in a group and this is, after all, this theta is a group element. Okay, so now what is this? This again is an element in A of S. That means this again is a permutation and after all is a function from S to itself, and A is an element in S. So this a theta to the power I is the image of A under this function theta to the power I. Because we are writing inputs to the left of the function, so it looks like this. And if that happens to be B, then we say that A and B are related. Note one thing, that A and B are our choice. Theta is fixed, but this I can change, this integer. If there exists some integer for which this thing happens, then we say that A and B are related. Now our next thing is that this actually is an equivalence relation on S. That's what we have to see first. We claim that this defines an equivalence relation on S. To verify that, you have to verify those three familiar things. You have to verify that this relation is reflexive, symmetric and transitive. For these three things are of course true. Any element A in S is related to itself, since A is equal to A theta to the power 0, that is equal to AE. Okay. In the group A of S, what is the zeroth power of any element? By the definition of integral powers in a group, The zeroth power of any element is defined to be the identity element in the group. The identity element in A of S is the identity mapping on S, which does not change anything. So this theta to the power 0 is the identity map on S, and so it does not change A. A stays A itself. And this E that Herstein has written here is actually the E you have in A of S, that is the identity map on S. When you apply that on A, the result is A itself. So this equation is now true with 0 in place of I. So there is an I in this case, and that is why any element is related to itself, and so the relation is reflexive. Number 2, if A is related to B, then of course B is equal to, by definition of this relation, A theta to the power I for some integer I. So A is equal to what? A theta to the power 0. Again, we have already seen this, and now theta to the power 0 can be written as theta to the power I times theta to the power minus I, because this, according to the rules of exponent in the group A of S, will give you this. Now, because this is composition of mappings, A theta to the power I, theta to the power minus I, but A theta to the power I is B theta to the power minus I. So just like B is the image of A under some theta to the power I, where I is an integer, A is also the image of B under a power of theta, where the exponent is minus I, that is also an integer, which implies that B is related to A. So the relation is symmetry. And next, transitivity. If for transitivity, of course, we need 3 elements not necessarily distinct in S. Such that A is related to B and B is related to C. Then P is the image of A under some power of theta, and like that C is the image of B under some power of theta for some integers I and J. But then C is B theta to the power J, which is A theta to the power I theta to the power J. By the definition of composition of functions, this is A theta to the power I theta to the power J. by one of the rules of exponents in the group A of S, this thing is theta to the power I plus j. Because I and j are integers, I plus j is also an integer. So C turns out to be the image of A under some power of theta again, where the exponent is an integer. Whence A is related to C. So the relation is transitive. Being reflexive, symmetric and transitive, it's an equivalence relation on S. And therefore, by the first theorem of this text, theorem 111, this relation decomposes S into disjoint equivalence classes. This equivalence relation by the very first theorem induces a decomposition of S into disjoint subsets. Disjoint subsets, namely equivalence classes. We can just simply write directly disjoint equivalence classes. Now we are going to give a new name to these equivalence classes. They will be called orbits. I will try to justify the name. Let's first see what Herstein has to say about them. We call the equivalence class of any element small s in capital S the orbit of small s under theta. Keep in mind that the equivalence relation we have defined is not really exactly one equivalence relation. It is one equivalence relation as long as we keep theta fixed. You take any other theta, which of course you can do, because in the group A of S there are almost always many thetas. The entire thing will change. So that's why we say not just the orbit of S, but orbit of S under theta. Thus, the orbit of S under theta consists of the elements which are of course related to S. That means by the definition of our relation, the elements look like this: S theta to the power I, because S theta to the power I, where I is any integer, is by definition related to S, where I can take all these integral values. Okay, now I briefly say why this would be called the orbit of S. In place of S, you see, what does a permutation do actually? A permutation actually changes an element, or rather, if you look at the entire set S globally, then it changes the arrangement of the elements of S. That's what we know ordinarily by a permutation. So it's like a force which changes the position of the particles or whatever object you have in a physical system. It moves them around. For example, like the planets in our solar system, or for example a comet, okay, which may pass by the solar system. It may enter the solar system and it may leave. It may come back after several years, or it may come only once and to never return actually. That can also happen. So the celestial body, whatever it is, whether it's a comet or it's a planet or some sort of satellite, is S, and the force that is acting on S is theta, or rather the several powers of theta. Or you may think of the powers of theta as the force at different instances of time. So as the forces act on S, its position changes and it takes different positions. So those positions trace out a path, that is the orbit. So in that sense, you can think of this equivalence, the elements in the equivalence classes as different points in the orbit. Maybe that's why it's called an orbit, the orbit of S. Now, why I said not just simply some closed orbit, but I told about that comet also, which may come only once, never to return. It's because it may happen that, say you keep on increasing this exponent I. So first you see what happens to S if you apply theta to S. So you get the element S theta that corresponds to a new position in the orbit. And then again on S theta you apply theta once more. So the force is, it continues to act on the body. So you get S theta square, another new position. Now these elements that you are getting, these new elements, S theta square, S theta cube, like that, these elements may not return in the sense that you keep on getting distinct elements without any end. This will happen particularly if, I can't say this will happen, this may happen if S itself is infinite. If S is finite, then of course that cannot happen, because all these things are in S. So if S is finite, something after some time must repeat. That repetition is like coming back, like a closed orbit. Okay, so that's why I drew, while drawing this analogy between actual physical orbits of celestial bodies, I brought in that comet example also. There may be open orbits, okay, which never end, and there may be closed orbits also. And that's what the author is now going to say. In particular, if S is a finite set, if S is a finite set and our celestial body belongs to S, then there must be repetition, and that repetition will itself continue as many times as you want, because it will go like this now. So that same position will occur over and over and over again, but it will occur for the first time at some instant. So there exists a smallest positive integer L, which of course would depend on this on the particular celestial body we have chosen in S. So it is a function of S, it depends on S, depending on S. Such that we are drawing these analogies from classical mechanics just for the sake of somewhat justifying these interesting names, orbits. But at one point we will actually have to go to classical mechanics. I don't know when that will happen, but I hope it will happen. Okay. Before that, we have to, of course, finish some significant differential equations, both ordinary and partial, and then we will go to those parts. They are extremely interesting. Such that the body is brought to its original position after some L times the force acts on the, after some L instances, at the Lth instance the body comes back. Now, if you are thinking why this would happen, just forget about those analogies, celestial bodies, all those things. If you rigorously mathematically try to see why that would happen, that is because you just think of these things. The effect of the positive integral powers of theta on S. And this list cannot go on indefinitely because all these elements must belong to S. So there should be some repetition at some point. That means some S theta to the power I should be equal to S theta to the power j. We don't really know when this will happen, but somewhere there would be some repetition because of finiteness of S and because all these elements being in S. And say I is less than j, then if you apply the function theta to the power minus I on both sides, use all the usual rules for calculating with composition of functions, you will then get on this side the image of S under the function identity function, that is theta to the power 0, after applying theta to the power minus I on both sides. So that means the left hand side will be S and the right hand side will be this. So you see that j minus I is a positive integer, and there exists a positive integer for which this corresponding power of theta does not change S. So if there is a positive integer, there would also be a smallest such positive integer, because positive integers are well ordered. So that smallest positive integer is L. Okay, so that way you can rigorously justify that there is one such L. Now if this happens, the orbit of S under theta then consists of precisely these elements: S theta, S theta square, like this, up to S theta to the power L minus 1. Note that if L is 1, then you just have one element, that is S itself, in this list of elements, but they are finite in number, and you can in fact go to higher powers. If you go, all the things will be repeated, and the repetition will continue happening again and again. So these are just all the elements in the orbit. So because the orbits are the equivalence classes, so these elements will form the equivalence class that will contain the element S. And these S theta square, S theta to the power L minus 1, all these are some other elements of capital S that belong to this same equivalence class. They are equivalent according to our definition of equivalence relation. Now we say something new. We call the ordered set consisting of these elements only, but written in this particular order. This ordered set is a cycle of theta. We don't know, at once we don't understand why Herstein has decided to suddenly think of an ordered set. We will see. Okay. Now note that there is a very big difference between an orbit and the corresponding cycle, because a cycle, the way we have defined it, is coming directly from an orbit. One difference is, of course, the orbit is just simply a set, this set. But this being a set does not care in what order we decide to write the elements. So you can in fact write the same set like this, or in any other manner whatsoever, the orbit does not change. However, because the cycle is an ordered set, the order matters, and that's why we are using the round brackets to enclose the elements, because that's how we generally denote an ordered n tuple, or in this case an L tuple, that which looks like a vector having L number of components. But there is one more thing here. It is not just simply a vector. There is something else which the author has not mentioned explicitly, but it is there. The thing is that this ordered set is not just simply a tuple or a vector, but it is actually this. You can in fact start with not just S. I mean, it's not absolutely necessary to start writing this notation with S. You can in fact start with S theta also, for example. But if you do, then you have to follow that up with S theta square, S theta cube, and so on. You would go up to this, but then you have to write S. There is no difference between this cycle and this cycle. That is something the author has not said explicitly, mentioned explicitly. Note that as vectors, these two things are totally different, because the first component here is S, here the first component is S theta, and depending on S and theta they may not be the same thing, but as cycles these two things are the same. To summarize this somewhat peculiar convention, we can say this: a cycle is an ordered set in which it does not matter where you start, but you have to maintain the cyclic order. Okay, if you can in fact start from here also, but then immediately you have to write S and then S theta square. So the thing actually looks like this. If you envision this, if you think of it as really like a garland, and these are the beads forming that garland, then a cycle is actually this: S theta, S theta square, S theta to the power L minus 1, and then the next one is this. Okay, or if you want, you can view, you can look at this from the other side of the board, then the orientation will change. But the point here is that this cyclic order should not change, and in fact this is what matters. But because it is difficult and cumbersome to make a notation which looks like a circle or a cycle, so we write in a more horizontal manner like this. But it does not matter where we start. Okay. Now comes the question of, fine, orbits, we understand what orbits are. They are, after all, the equivalence classes of our equivalence relation. But why suddenly cycle, and why suddenly that relation, in fact, in the first place? What is its purpose in all these things? We were discussing permutations, and suddenly out of nowhere we decided to define a relation. We showed that it's an equivalence relation. granted that theta has been used in that relation, but all of these things look quite artificial, and frankly speaking, we don't really understand where we are going with all this. So that will become clear as we move forward. Now the next comment is, this part of course is not there in the text. If we know all the cycles of theta, then we clearly know theta, for we know the image of every element of S under theta. Now don't forget that the cycles are after all coming from the orbits. So we can in fact draw a figure like this. This is actually our set S, where we have all the elements. On this set we have the permutations acting. Each permutation is rearranging the things in this set. And now our permutation is theta, or rather because we are considering the orbits, so our permutation actually involves not just theta but powers of theta. So the orbits are the equivalence classes of our relation. So it will decompose S into disjoint sets. So this is one orbit, this is another orbit, and each orbit, say this is S, it has all these things, S theta square, etc. Many other elements, who knows how many, S theta to the power L minus 1. Another orbit will have some other elements totally different from these elements, because the orbits are equivalence classes, so they are disjoint, there is no common element. Say it has T, then T theta square, many other things, and then T theta to the power L minus 1, but this L is different, some L prime which depends on T, just like L depends on S. So we have all these things like that. All the other orbits are there. They are orbits in the sense that theta and its powers locally act on these parts of S, that it moves around the elements of this part but keeps them in closed compartments. That's why they are called orbits. Now each such orbit gives us a cycle. This orbit has given us this cycle. This orbit, for example, will give us this cycle, T theta square, etc. T theta to the power L prime minus 1. And other orbits will give us other cycles. Now what we are saying, or what rather the author is saying, if we know all the cycles coming from all the orbits, then we know everything about theta. Why? Because we would know the image of every element of S under theta. Okay, let's just look at that statement for a moment. Every element of S under theta, it will go to some image, and now we know that image if we know all the cycles. That is because if you take any element, say you have taken some element here itself, say just for the sake of argument you have taken T theta cube, Now we are saying that we know the image of t theta cube under theta. Why? Because that image is nothing but t theta cube theta, that is t theta to the power 4, and that thing is available here. And in fact, the order in which we would write these things, that would tell us what this image is under theta of this element. Of course, when you have an actual set S, there you have actual elements, you won't see them as S theta, they won't look like that, they will just be some elements. So once you look at the cycles, you will know which element is sent by theta to which element. So in that sense, we know all the images. And why all the images? Because the orbits form a decomposition of S. So it covers, all these equivalence classes cover S entirely. So every element will appear in exactly one orbit, and so by looking at the cycle corresponding to that orbit, you will find that element somewhere in the cycle. Where the element or the symbol in S appearing next to this element on the right side is the image of this element under theta. Why? Because that's how we have chosen to write a cycle, and that is why you can see that it does not matter where we start, only the cyclic order has to be maintained. That's what matters. So this statement is justified. If we know all the cycles of a permutation, then we know the image of every element under theta, under that permutation. There is one more thing that I must mention here. Note that this is the orbit of S, okay, but this at the same time is also the orbit of S theta. Why? That is because the orbit of S by definition should contain S, and that is because our relation is reflexive, and the orbit of S theta also contains S theta, but at the same time the orbit of S contains S theta, and the orbit of S theta contains S, and these orbits are equivalence classes. So they either they are distinct, either they are identical or disjoint. Since the orbits of S and S theta are not disjoint, they have to be identical. So finding the orbit of S automatically finds all the orbits of the other elements also in that orbit. Now what I am trying to say here is, you look at the way we have named things. Orbit of S under theta is something that depends on S and also on theta, of course, but the cycles of theta, when we are speaking about the cycles of theta, we don't give any reference to any S or any element, because theta has cycles, and in it all the elements will appear, all the elements of S will appear, and that too in a manner in which if you find all the cycles, you will actually find all the symbols in S into distinct groups, where there is, you can say that the cycles are also disjoint, in the sense that two different cycles, two distinct cycles will not share any symbol. There won't be any common symbol. Okay, fine. So we have got this far, and this is quite far. We have come without any we have not still got anything in return from all these abstract exercises. Where are we going with all these things? Okay, now comes the Now all this labor will pay off. Oh, but before we go to that idea which would show why these things are important, there is one example, of course, illustrating these things, because we have so far been talking about these things in an abstract manner without taking an example. No. So before proceeding, we illustrate these ideas with an example. So if you have understood what I was rambling about here, then the example should be clear. Let us take a permutation theta, a concrete permutation. Two, 1, 3, 5, 6, 4, where the underlying set S on which this permutation acts consists of the elements one, 2, 3, 4, 5 and 6, and it's very easy to forget these things. Remember that 1 is not actually the number 1 but the suffix 1. So 1 stands for x1, 2 for x2, etc. So what are the things we have seen so far? We have seen that equivalence relation. We have then seen the equivalence classes which we are calling orbits, and then using those equivalence classes we have defined some cyclically ordered sets known as cycles. So let's calculate the orbits of the elements here in S under this particular theta, starting with 1, the orbit of 1 consists of the images of 1 under the integral powers of theta. If you want, you can see why 1 is in the orbit, because 1 is related to 1. Then the image of 1 under theta, that is 2. then the image of 1 under theta square, which is the image of 2 under theta, because 1 theta theta, 1 theta is 2, so image of 2 under theta is 1. Again we have come back to 1 already in 2 steps, and in the third step we have come back to 1. If you treat this one also as a step, thus the orbit of 1 consists of just 1 and 2. It's the set formed by 1 and 2. The orbit of, okay, see, orbit of 1 consists of 1 and 2. That means the orbit of 2 also is 1 and 2, because 2 belongs to that same equivalence class. So if you now try to find the equivalence class of 2, because of the fact that distinct equivalence classes are disjoint, so the equivalence class of 2 will also be this thing only. So there, that we don't have to do. So we look at 3. The orbit of 3 consists just of 3 itself. And why is that so? Since 3 theta is 3, so it does not matter what other powers of theta we decide to look at. If all of their effects on 3 will be just this, we are not going to get anything new. The orbit of 4 consists of 4, of course, then 4 theta. 4 theta is 5, then 4 theta square. 4 theta square is 5 theta. 5 theta is 6, and 4 theta cube, which is 4 theta square theta, that means 6 theta. So we have come back to 4. So that is the equivalence classes, or the orbits are these. One orbit is this, another one is this, and another one is this. So now we can write the cycles also. Okay. Again I am repeating, because the cyclic order just that needs to be maintained, you can write in place of this, you can write 2, 1. These two are the same cycle. 3, of course, it has nothing else to it. Here you can write 5, 6, 4, or you can also write 6, 4, 5. 4, 5, 6, 4. 4, 5, 6, 4. 4, 5, 6, 4. So the cyclic order has been maintained. So the same cycles can be written in several different ways. nothing will change. Now next comes the thing that will ultimately justify why we are stressing so much on cycles. Why are we emphasizing cycles so much? It seems like our if we are given a permutation, we just somehow are very keen on calculating the cycles. So what comes next, that will show why cycles are important and actually what is their relationship to the permutation. I mean, you of course you have got the cycles from the permutation, but can we somehow retrieve the permutation back from the cycles? That's what will come next, which however I won't do in this video today. So it will be done in the next video. So I am going to end things here for now. So we will see where we can go from here in the next group theory video. Tomorrow is Saturday, no? So tomorrow we have again, and the previous Saturday we solved Galilean's exercises. So tomorrow there will be exercises from abstract algebra by Grigory T. Lee, and on Sunday of course we have our analysis. So with that I sign off. See you tomorrow with Lee's exercises. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.